The Intermediate Value Theorem, sometimes abbreviated IVT, is a fundamental principle in calculus that guarantees a continuous function doesn't skip output values. The general idea is that a continuous function on a closed interval must hit every value between the values at the endpoints of the interval. Let's consider the formal mathematical statement of the theorem. Suppose that the function f is a continuous function on the closed interval from a to b. If L is any value between the output values f of a and f of b, then there exists at least one number c between a and b such that f of c equal L. A diagram always helps with understanding. Suppose that the function f is a continuous function on the closed interval from a to b as shown. Let L denote any value between f of a and f of b. Then there must exist a number c between a and b, where f of c equal L. There are two critical requirements for the Intermediate Value Theorem to be applicable. First, the function must be continuous on the closed interval. If there is a hole, jump, or vertical asymptote, the function could skip over the value L. And second, the target value L must be between the values of the function at the endpoints of the interval. That is, L must be between f of a and f of b. Let's consider a few uses of the Intermediate Value Theorem. First, if f of a and f of b have different signs, meaning one is positive and one is negative, then there must be at least one point c between a and b where f of c equals 0. This is the most common use of the theorem, finding zeros of functions. In fact, the Intermediate Value Theorem is the basis of the bisection method by which computers estimate solutions to equations. In another example, if f of a is 4 and f of b is 1, then there must be at least one point c between a and b for which f of c is 3. Similarly, if f of a is 4 and f of b is 1, then there must be at least one point c between a and b for which f of c is 2.5, or any other value between 1 and 4. Finally, if f is continuous on the closed interval from -1 to 2, with f of -1 equal 3 and f of 2 equals 0, then there must be at least one point c between -1 and 2, for which f of c is 2. Let's consider another typical problem. On which of the following intervals is the function f of x equal -x squared minus 4x minus 2 guaranteed to have a 0? The interval from 0 to 2, the interval from 3 to 4, the interval from -3 to 0, or none of these. Since the function is polynomial, it's continuous everywhere and therefore continuous on every closed interval. Using the Intermediate Value Theorem, we just need to see if the endpoints of the related closed intervals have function values with different signs. For the closed interval from 0 to 2, we see that f of 0 and f of 2 are both negative. Therefore, the Intermediate Value Theorem does not guarantee a value between 0 and 2 with f of c equals 0. For the closed interval from 3 to 4, we see that f of 3 and f of 4 are also both negative. Therefore, the Intermediate Value Theorem does not guarantee a value between 3 and 4 with f of c equals 0. Finally, for the closed interval from -3 to 0, we see that f of -3 equal 1 and f of 0 equal minus 2. Since 1 and minus 2 have different signs, this time the intermediate value theorem does guarantee a value of c between minus 3 and 0 with f of c equals 0. Let's consider one final example. Is there a guaranteed solution to the equation minus x plus 2 sine x plus 2 cosine x equal 1 on the closed interval from minus 2 to 1? Since the function minus x plus 2 sine x plus 2 cosine x is a combination of continuous function, it is continuous everywhere. Thus, f of x is continuous on the closed interval from minus 2 to 1. Using a calculator, we see that f of minus 2 is approximately negative 0.65, and f of 1 is approximately 4.76. Thus, the intermediate value theorem does guarantee a value c between minus 2 and 1, with f of c equaling 1. That c value is a solution to the original equation.